Okay, good afternoon. So let's continue the school with the third class of Dr. James Jenkins.
Thanks, Marcel. Well, thanks for coming again. I have the unenviable task of giving the first talk not only after lunch when everybody's tired and has a full belly, but also coming straight after a talk on sex. So this is definitely not as exciting, but I'll try and make it sound so. Okay, so we've been kind of building up this picture of planet formation, star formation from a theoretical standpoint, and also observationally. So my job here is to try to convince everyone that we're on the right path to build the population, the kind of galactic population of exo-Earths. And so I've been discussing first what we use, what techniques we use, the methodologies, and we have a few. I convinced you this is not all about radial velocities, even though I'm heavily biased, because that's what I do, and that's what I believe is really going to give us those first exo-Earths around at least the nearby stars. But then I showed what we've learned about the population, and what types of planets we've been detecting over the past 20 years, since the first planet was detected. And now I kind of want to move away from the introduction and look at the challenges that we kind of face. What challenges do we have to overcome and have been overcoming over the past 20 years, but what more do we need to overcome if we really want to dig out those signals from exo-Earths? In particular, exo-Earths orbiting the Sun-like stars. I'm going to look at M-dwarfs as well. But M-dwarfs, I tried to convince you, and I'm going to continue to convince you, that we're basically almost there with the M-dwarfs. We're almost there because of a few key reasons in particular. And when I say we're almost there, it depends how we define these exo-Earths, of course, and we're going to discuss that tomorrow in the panel session. And we've been looking at how we define exo-Earths, how we define the habitable zone. But one thing is, those M-dwarfs are small, things like about a tenth of a solar mass, such that they're habitable zones, or they're classical habitable zones, where we can move an Earth-like planet and plonk it in an orbit around them. That habitable zone, where they could maintain liquid water over long timescales, is much closer to the star. And remember, both transit and radial velocity methods are heavily biased to planets very close to the star. And so I'm going to convince you both kind of today and more tomorrow when we look at some real systems that we've detected, and I plan to kind of give you some new results that we're going to publish very soon. Since giving some talks here, I wanted to give you some new discoveries that no one else has seen yet, and we're going to try and publish. But I'm going to convince you also that these things, the M-dwarfs, we're already there. We're getting the kind of super-Earths. We're getting to the one-Earth masses around M-dwarfs in the habitable zone. So this is a really exciting time. And finally, we'll get to tomorrow as well, the kind of future. So in these two classes, I want to look at the challenges and how we're going to overcome the challenges, and already are overcoming the challenges, and to detect the population of exo-Earths. Okay, so what challenges are there? Well, maybe it seems obvious, but there's two main, bracket this as two main populations, or at least two main subjects, and that's the stellar physics and instrumentation. And when I say the stellar physics or the stars, what I'm really worried about are things like rotation, magnetic activity, and convection, because the interplay of those three physical properties give us a lot of problems when we look for planets. They introduce a lot of noise into our measurements in various ways, and we're going to see those various ways in the sense that there's a strong connection between rotation and magnetic activity, but also just the presence of that magnetic activity on the surface of the star introduces, or let's call them spots. We're going to see what spots are in a second, but those introduce problems into our radial velocities in the sense that we can sample those, or the effect of those spots, in our spectra and in our photometry. And the fact is that we're going to see that they can be modulated by rotation. And so when they're modulated by rotation, not only are they giving us a problem by introducing noise, but they're also introducing signals. And the bad thing for, I say the bad thing, one of the problems for us is that the rotation of kind of old stars, like the Sun, quiescent stars, turns out to be in the ballpark of 20, 40, 50, 60 days. Something in that kind of ballpark. That's the rotational period that they have. And that's a nice region, particularly for low mass stars, like M dwarfs, early M dwarfs, late Ks. That kind of region is where we're in the habitable zone. So one of the problems are that we can introduce signals, and this has been done, and they've been published as planets and later retracted and shown as being only magnetic activity. One of the problems is that we have to be sure, ultra sure, very confident at least, that what we're looking at is a Doppler signal. Remember, for radio velocities, we talked about the Doppler effect. We need to be really sure that what we've got is Doppler. All of these lines are moving at the same time. They're stable over long time scales or long periods, both amplitude, phase, and period. Nothing's varying. And so I'm going to try and convince you through today how we can do that. What methods do we have to prove that, or be really confident that what we're looking at is a Doppler signal and not just the actual surface of the star, the magnetic activity. And convection as well. Convection, we'll see in the next slide. Well, I'm not going to say much at the moment, but convection is another source of error we have. And then just in a few slides at the end, I will start to discuss instrumentation. More going to discuss instrumentation tomorrow, because this is really what's going to drive the field in the future to really detect these XORs. The new instrumentation that's coming online, and not just by radio velocities. We're at a very interesting time now where I think we're kind of seeing a convergence of instrumentation. Both radio velocities, transits, astrometry, direct imaging, they're all beginning to get to the point where, remember in the first class, well actually we can't remember because I couldn't draw it, it's too dark, but we were talking about the biases. And I was saying that things like, I'm going to point to nothing here but make it look a bit more interesting. I was saying that things like the direct imaging method can sample things well when they're far from their star, and similar to astrometry, but the radio velocities and the transits are really close to the star. Well, that's kind of been problematic, but now we're getting to, or tomorrow, I hope I can convince you that we're getting to the point where that technology is beginning to overlap. The phase space is beginning to overlap. And that's really important because we've seen yesterday, for instance, what we garner, what we gain when we can get both transits and radio velocities, for instance. We get densities. We can then apply models and get bulk compositions. So building up things like the mass-radius relationship of exoplanets is super important, even particularly for the low mass planets, because, like I said, we can start to look at bulk densities then. So, in a few slides today and more tomorrow, we'll look at a little bit of problems of flux, instrumental stabilities, and some extreme calibration. So, just to introduce, and I won't say a huge amount here because Fred already showed over his classes some of these equations. This is more for your own, for you to take away, that this is our basic structure of a star, where, so a sun-like star. I'll explain a little bit more when I say that. Where we've got, and Fred mentioned this, we've got a core that's producing, we've got nuclear processes in the core, where temperatures of 10 to the 7 Kelvin or so, under high pressure. Then we get about 70% of the rest of the star is radiative. So that part of the atmosphere is like a radiative process. And then we get to the last 30% or so, that's convective. And the convection is one of the issues that I want to discuss as far as an observer like me looks at for radio velocities, for radio velocity precision. And these equations, of course we've got things like hydrostatic equilibrium there, and this is interesting because these stars are kind of self-sustaining systems over long periods of time. we call them stable. We say that when we're on the main sequence, the star's stable. It's a stable star. The Sun, for instance, is going to sit there for about 10 billion years. Now that's great for the emergence of life and the long sustaining development of life. If we discussed about complexity, whatever the hell complexity is, at least we believe intelligence is developed here after about 4 billion years or so. And the hydrostatic equilibrium, remember, we're fusing in the core here. We're turning 4 hydrogen atoms into a helium atom or a couple and losing energy at the time. So what's happening is that in the core we're changing its composition. And so the star's actually heating up through its 10 billion years. So it was something like 20% or so, it's changed by about 20% in temperature. It was a bit cooler when it made it onto the main sequence. And so basically the Earth had to be it was under different conditions. But this war, this kind of fight between gravity that's trying to collapse the star and the outward force of pressure from the core that's being produced by these nuclear reactions is kind of self-sustaining over long periods of time. So the core kind of grows a little, gets a bit hotter, the star inflates itself a little. So I'm just trying to convince you that we kind of understand stars. Actually, we understand them very well, and we understand their long process, but they're still dynamical bodies. That's the point here. They're dynamical bodies. So I said in the first class that we can measure stars to 1 meter per second or so precision. We can measure their acceleration, their velocity in space with a precision of 1 meter per second, less than your average walking speed. And that's quite incredible when we consider that there's something like this massive body that's kind of dynamically stable in some respects, but really when you look at its surface, it's not stable at all. And I just wanted to highlight here, I've been talking about kind of what we call the photosphere or so. The kind of, let's say, the inner structure of stars. Remember, these things don't have solid surfaces. They're just big balls of gas, big balls of plasma sitting there burning away. But their atmosphere is also composed beyond the photosphere. For instance, and I just want to highlight this, there's an area called the chromosphere. And the chromosphere is quite important for ourselves in that in the chromosphere certain lines form that track magnetic activity. In particular the calcium H and K lines. And I'll show you in a second what those are, so I can give you a view of some Michel spectra as well, which I realised I hadn't really done in 2 classes discussing radio velocities. So there's the chromosphere, but then look at this transition. This is really interesting. And this is temperature. We've got a log scale of temperature here and height above the photosphere. So height above what we would define as the surface, the optical depth of about 2/3 or so. We see there's a massive rapid transition to something we call the corona, the nice part that we see when we look at when we see eclipses. We can see these nice features that emerge in the corona. And you can see that we go from something like 6,000 Kelvin at the photosphere all the way up to over 1 million Kelvin. So this is a massive transition region between the chromosphere and the corona. So I want to show that we're looking at the surface of the star. We're going to discuss convection and the effects on radio velocities, but hell, the Sun and we believe other stars have got a lot more constituents in their atmosphere. Constituents that we can use to track, for instance, their activity levels and understand what they're like when we look at them with radio velocities or photometry to look for transits. And so here's just a nice little GIF of that photosphere region, the region that we class as the surface of the Sun. And we can see these kind of patterns here. So what we're seeing is really like hot and cool regions on the surface of the Sun. This is the convective pattern or the granulation pattern. So when you hear anyone talking about the granulation pattern, this is what they're talking about. This small-scale movements, these small-scale velocities of hot and cold gas that we can see on the photosphere. And we can look at the typical granulation size, and it turns out to be about 1,000 kilometres or so. You'll see why that's important in a few slides more when I talk about radial velocities, but it turns out to be 1,000 kilometres or so. I showed Europe here since I'm Scottish. I know I'm down here in South America, but this is just to give you a look at scale. But one of the more important points of that, although they're fairly large, at 1,000 kilometres, they also have a lifetime. They also have a lifetime of about 8 minutes. And you'll see why that's important in a few slides when I talk about how we're going to remove that signal from the convection. And so what I wanted to show here is, I know probably most people have seen this before and understand, at least the astronomers will understand convection to this stuff. But we can kind of parameterize convection at some level, where we have some kind of parcel of gas, of plasma. We take a parcel, we immerse it in this fluid that's got some density and pressure. And what we can do is we can look at that parcel. If we say it's isolated, we can move that parcel, or at least look at it, how it moves in this fluid. We can expand it, for instance, and expand it adiabatically, given that probably, I mean, the dynamical timescale will be faster than the thermal timescale, and so we can then look at, or at least parameterize, how convection works, how it moves, in the sense that eventually, so remember that inside stars, we've got a massive pressure temperature gradient, so temperature will change by something like 4 orders of magnitude, or something between the core and up to the surface. Pressure is much bigger, something like 14 or so orders of magnitude difference. And so we've got a big change here, but eventually, if we look at this parcel and we expand it adiabatically, either if the stellar density is greater than the parcel, it's going to drop. I mean, if it's less, this thing just buoyancy forces, it's just going to continue to infinity under these conditions. Eventually though, if we're in the case where we get some kind of equilibrium state, what we're going to see, we see something that we characterise as Hadley cells or so, where we get a cell where we have this kind of hot kind of package parcel that's going to come up, and they move and they start to circulate under these conditions. And the reason I'm saying that's important is because then we see a velocity, and it's not a uniform velocity across the sun. Here, this is colour-coded in velocity on the solar disk. So there's something called convective blue shift. So when we integrate this pattern, all these little motions, so we see these cells, we've got this hot package coming up, and remember, if it's hot, it's producing more photons, it's giving off energy, compared to when it cools, it reaches equilibrium, cools and drops. So we see, this is this granulation pattern, and so here we're receiving more flux from these things moving up, and then they cool and they drop down. And so, because we receive that, we're receiving more flux from a package or a parcel of gas, of plasma, that's moving towards us. So it's moving towards us, and remember we looked at the Doppler effect in the first class, and so because we're receiving more flux from material that's moving towards us, we're going to see in our spectra a little movement to the blue. We're going to see a shift, a convective blue shift. And that's nothing to do with the actual movement of the star, it's just this dynamical process that's going on in the convective envelope. And so that's something we need to take care of. So just to give you a nice image, I've not really given very nice images over the two. Like I say, I work in spectroscopy, we work on lines. So this is probably a kind of photo, an image that everyone here is familiar with and seen. And the important point I just wanted to highlight is we get this kind of nice illumination, uniform disk. It's not quite uniform. Of course, we have something that kind of gets darker, limb darkening effect it's called, which becomes important when we look at transits and we try to fit the signal of planets from transits. We have to deal with the fact that there's a kind of darkening effect as we get to the limb. And then, but more importantly for what I'm looking at today is these regions, these spot regions. And these spot regions can be quite large. If we compare that to the size there, they're on a par, some of them on the Sun, with the size of the Earth. So these are large spot regions. Now, the question is, what's driving these spot regions? Or what's driving this whole magnetic activity, or how it affects our radial velocities? And we can see in some other images here that what we're seeing are magnetic field lines. And those magnetic field lines are associated to the spot regions. In particular, what's happening is, what we believe is happening is that we're getting strong magnetic field lines that are kind of bursting through this surface, or bursting through this photospheric layer. And because the magnetic field lines are kind of bursting through here, the toroidal field lines, I'll show that in a second, it's driving a kind of less efficient convection. And so although that spot region looks black, it's still a few thousand Kelvin in temperature. It's only that it's a few thousand Kelvin less than the surrounding material for that reason. And so we can kind of look at a simplistic model for the magnetic field of the Sun, or stars in general, where we just consider it as kind of two components. One, a toroidal component and a poloidal component. So, meaning this poloidal component is kind of like a big bar magnet, or a dipole model here that kind of spans all the way around. And then we've got a smaller toroidal component where the field lines emerge and they quickly dive back into the star. And we have a model to describe that we'll see in a few slides more. But when I'm talking about the magnetic field, or talking about the magnetic effects that we're trying to deal with, this is what I'm meaning. I'm talking mainly about the toroidal field at some level. And it's interesting to look at what that means at some level, in the sense that we've known about this for at least the spot patterns, some of the first observations we were ever doing. And we get these lovely graphs, these butterfly diagrams, where essentially we map and count the number of sunspots. That's all we're doing. And we find a few things interesting about that. One, so this is time, and we're looking over long time scales here. But what we see is that the spot patterns tend to be, they tend to emerge and end up around kind of the solar equator, if we want to say that. They're confined to plus or minus 30 degrees or so, like latitude bands. So that's something that we need to explain if we want to model the solar magnetic field. So there's bands, there's latitudes, and there's also, we can see, more importantly, cycles. That's one thing that I'm getting across here. That's more important for what we do as exoplanet hunters, using particularly radial velocities. We can see that we have these little cycles, and the cycle, where if we look at the counts over time, what the main cycle that we see turns out to be 11 years or so. We get a solar cycle of 11 years or so. But also positions and stuff of where the spots are emerging changes through that cycle. So although there's cycles, we also need to think about how much of the surface of the star is filled by these spots. That's called the filling factor. So we can think that if the filling factor is higher, if there's more spots emerging or more spots on the surface, I'm going to show that we'll have a higher impact on our radial velocity. It'll make it more difficult for us to find these exo-Earths. We want completely clear stars. We want super quiescent stars to find exo-Earths. But one of the other things we can do is actually look at the field strength, running from minus 10 to 10 Gauss or so. And we see other things that confirm these cycles. We see polarity reversals, for instance, running from, like I say, -10 to 10, where the field's shifting polarity. So we're very confident, let's say that we have strong magnetic cycles that we know now are impact negatively from my perspective. And I guess this is the one person's junks, another person's gold or whatever. For me, this is junk, and it's junk I need to deal with. And how can we deal with it? Well, I said I was going to show some spectra. This is the first time I've showed any real Echelle spectra. And we talked about what Echellograms, or at least what the instrumentation is in the first class. And important in this region, this is in the kind of blue optical part of the spectrum we're looking at now. And look at the resolution here. And this is only about a resolving power of about 50,000, just for a round number for you to think about, because I'm going to talk about things at over 100,000 today and tomorrow. But this is not noise. Each one of these little things are actual atomic lines. And mainly in the sun they're iron. So these are mainly iron lines. However, look at these guys here. These are the calcium 2H and K lines. And the calcium 2H and K lines have got a long history in astronomy from observing the kind of parameterizing or observing the magnetic field of the sun. And now we can do this on other stars. And I'm going to show why, because there's something, if we look back here, and we just look at radiative transfer, we can look, there's something called the source function. And the source function kind of defines where the lines emerge, where parts of the lines emerge. And so if we look here at the optical depth, or the depth in the star, or the sun, against the source function, we can see this rising trend here. With the optical depth, in the sense that if we look at the line, so now we're looking at the change in wavelength, or velocity, if you want to look at it in velocity, the change in wavelength from the line centroid against flux. What we see is that deep in the stars, or deep in the sun, that we find that's where the core of the lines emerge from. So the core of the lines emerge from higher, from different regions compared to the continuum. In the sense that, so let's think the continuum's deep and the core is high. And why is that important? Well, that's important because the core of the H and K lines, in this sense, form in the chromosphere. And because they form up in the chromosphere, they track magnetic effects at some level. The chromosphere is heated by these emerging strong magnetic field lines that emerge. The chromosphere is heated. And so if we look at wavelength against intensity or flux, we can see the effects straight away of that. So focusing in on those calcium H, one of those calcium H and K lines, we can see that we see this big broad line. And now if we're a quiet sun, what do we see is this nice deep calcium H and K line. It's nice and deep, nice and triangular shape as it goes down. Now, if we can stick our hand inside the sun and crank up that magnetic field, what we're going to do is start to heat parts of the chromosphere, and we're going to see reversal of that line core. Reversal because of things, when I say heating, things that track these spots, or the spot regions, we call plage. They're called chromospheric plage. And these are just hot regions surrounding these spots. And so what we can do is we can start to look, we can integrate. So this is a bandpass, it's a triangular bandpass. So we can just get rid of all this stuff here and integrate the flux in that line core. And we can compare it to the flux in the continuum around. So we're saying the continuum's stable, the continuum's deep, it's not in the chromosphere, it's not seeing the magnetic field effects, it's not seeing this hot region. like the core is. So we can integrate the flux in the core and compare it to the flux in continuum bandpasses. So the two lines, the two deep lines, the H and K line, we can simply integrate the flux and divide it by the integration of two bands, which the terminology here for historical reasons is V and R. We just integrate those two bands and take the ratio. And we do that as a function of time. And so I just wanted to show that calcium H and K, we don't put all our eggs in one basket. They're not the only strong lines we can use that emerge high in the atmosphere. There's other lines like H alpha. There's the helium-1d3 line. And we can use a combination of these to try and track the magnetic effects. So what I'm trying to convince you that we have tools. So maybe it looks scary at the beginning when I showed the sun, and it's kind of this big dynamical body running away at the upper atmosphere, and I'm showing all these lines emerging and going. So that looks slightly scary, but we do have tools. This is what I'm trying to convince you. We have the tools to try and deal with that to some extent, and to explore that when we want to look for planets, for low mass planets around nearby stars. So just to prove some level that we can use the calcium H and K index, this is what it looks like as a function of time. So we're looking at 20 odd years or so here. And we can clearly see that the calcium HK line, so the variation in that S index that I showed, clearly varies with the solar cycle. And we see it in solar irradiance. So if we just look at the flux as well, photometrically, we see the same pattern. So photometry traces the changing spots, of course, because they're dark and they're rotating. But calcium HK index is very sensitive to the presence of spots or magnetic fields and the presence of cycles.
I have you
Yep.
a question. When you look at the sun from the Earth, we said that it's a black body and the temperature is something like 5,700 degrees Celsius. What we're looking for? Or into?
So
the corona, the chromosphere?
It's the photosphere. So when we define the temperature of the sun, we're defining it at an optical depth of 2/3. That's where the optical depth of 2/3 is how we define the edge of the photosphere. That's what we actually see optically. If we look at the sun, what we're seeing is the photosphere. That's where basically the photons are emerging. That's where they've got less than, if we integrate across, they have less than one collision, basically, every photon. So that's what we see. It's about an optical depth of 2/3 or so.
It's not the corona.
So it's not the corona, it's not the chromosphere. We're looking, that's the photosphere. Anytime we talk about effective temperature of stars, we're talking about the temperature at things like the sun of an optical depth of 2/3. Yeah.
When you say about the flux, then flux where?
So, well, that's a point. We can look at the flux in many bands. So, in what I showed before, that's near we call it the blue optical or the UV. So, in those kind of bands, that's where we see these cycles much clearer. So it has these things have chromatic dependence, in the sense that. So one thing I'm going to discuss tomorrow is actually moving to the near infrared to do these observations, because in the near infrared, these magnetic effects, because they're really hot, they have less of an impact in the near infrared. And so that's one of the things I'm going to discuss tomorrow. Yeah, but the effective temperature is defined at the photosphere, so the tau 2/3. Finish that last slide? No. Okay. Well, just to continue on, I've been showing the sun, but of course we know the sun has planets. That's why we're here, right? So we want to look at other stars, and now I just want to convince you, and if things maybe start to look a bit more ratty, but it's not as clear in a lot of cases. But I just want to convince you that on some of these stars, again we're looking at time here against the chromospheric S index activity. We see similar cycles. We see cycles, magnetic cycles. And this was, of course, one of the drivers for using the calcium HK index or the H alpha index to map these magnetic fields. And I'll go into why we use them, how we use them. So, I want to show you the impact of these spot regions on radial velocities. And this is a nice paper by Ansar Reyners a couple of years back that shows this effect schematically. So, remember I said at the beginning, there's a kind of interplay between the rotation, the magnetic field, convection, but think particularly the rotation in the magnetic field, in the sense that, imagine we take a very simplistic model. And instead of, on the Sun, of course, we don't see a simplistic model. We see there's a blob here, maybe a group, then there's another blob here, and there's a blob there, and they're rotating. But you've seen also in that butterfly diagram that they're drifting. There's drift. But we take a simplistic model, we just take a disk and we say, okay, they're all in the same group. They're just one big black spot, one big dark spot. And we look at the stars also spinning. So we've got the spot coming towards us at some epoch. So if we say this star is rotating on a z-axis, tangential here, in the sense that here, this spot is kind of rotating towards us at this time. And so if we look at the spectral lines, what we're going to see is a deficit in flux on one side of the spectral line. Because of the presence of this spot, there's less photons emerging from the blue side, if we say, of the star. Gets to the centre, we just lose the flux in the centre, there's no impact. No impact for our measurements. We can still fit that with a Gaussian, and we'll still get the centroid we expect. But then when it's on the other side, of course, it's then moving, it's rotating away from us, it's redshifting. It's rotating away from us. And so we lose flux on this side. And when we look at that overall impact, we tend to see, well, we get velocity shifts. Look, this is 100 meters per second or so in certain impacts. Of course, we do this and kind of integrate all this stuff out. But still, when we look at it, and we try to integrate out over time in the best cases, we start to see that even quiescent stars are showing impact from the magnetic field or spots at the level of 1 or 2 meters per second. 1 or 2 meters per second. So we're at that level. HARPS, PFS, the spectrographs we've built, we've spent a lot of time to get us to that level, and we're now reaching basically the limitations of the stars potentially. Potentially. 1 or 2 meters per second. And remember I said that if we want to detect an exo-Earth, talking about a sun, an Earth going around a sun in the habitable zone, if you remember the number, it was an order of magnitude lower. It was 9 centimeters per second. So a lot of the stars potentially have magnetic activity effects, even quiescent stars, that's an order of magnitude above the signal that we're looking for. That means we need to really understand the stars. But we also have other tools to look at that. Because the flux is being eaten from either the blue side or the red side of the line, what that's going to do is introduce asymmetries into the line as a function of time. And of course we're doing time analysis. We're taking spectra as much as we can get of these stars and looking as a function of time, because we want to map out that Doppler signal, or that Keplerian signal that we've been looking for, that I showed in the first class. And so what we can do is we can just make some crude estimates. We can say, okay, I want to take one of these lines, or all of them combined, and just chop out maybe the top third and the bottom third, and we'll just take the difference between the top and the bottom as a function of time. And what that does is we can see that if we've got these effects like spots rotating, we're going to see some wobble, some variation in that. And that's what we see here. This is just radial velocity against time. Each of these curves are basically what we call, this is the bisector. And this is the classic C shape of the bisector for a sun-like star. And the bisector is just taking essentially the midpoint of our line sampling. And we can look and see, we actually see, if we look at the mean in dashed here of the sample, we can see that in this case about half of the lines that we looked at, or half of the cross-correlation functions, are red of the line and blue of the line. So what that means is the bisector, or the line shape, has kind of been swinging around as a function of time. And that was, we could correlate that with the radial velocities, and what that means is that in this case, this wasn't a planet, this wasn't a Doppler signal that we were looking at, or what Didier Queloz was looking at. This turned out to be activity. And the bisector, we call it the bisector inverse slope, has kind of became one of the strong tools we can use, even though it's quite crude, it becomes cruder for later type stars. It has this chromatic dependence. It's one of the key tools we've got to try and decorrelate radial velocities and line asymmetries, or from magnetic effects. And so, what we can do, now this may seem noddy to people, this may seem, I mean, what we try to do is look as a function of time at radial velocities just against like this calcium HK index, or this H alpha index, or this bisector index, and simply look for linear correlations. And so if we find linear correlations with time on between radial velocity and one of these measurements, then probably we can think to ourselves, well, that kind of puts up a kind of red flag that maybe the signal we see is not actually Doppler. It's likely to be magnetic. But that's only likely. We're scientists. We shouldn't talk in these kind of terms. What we really should be doing is modelling. And that's what we do now. And I'll go into that a bit later. But that kind of thing makes it difficult to publish in my field. Publishing a Doppler signal and showing a linear trend with one of the magnetic indicators makes it difficult to publish because people don't like it. People are scared of it, even if we try to model it. So, but the other thing we get, of course, we have large programs, ground-based, we've got space-based programs, but particularly ground-based programs of photometry, that we were looking at the population of sun-like stars and the population of M dwarfs as well. But we can get long-time baseline photometry. So remember I said the irradiance, we just look at the flux. This is what we do for stars as well. And we can take some stars and say, right, the biggest problem that I've just talked about is the rotation. Is that these spots, they're basically rotating around the star because they're fully dependent on the velocity of rotation of the star. So they're modulated by that rotation. So what we really want is to understand first order, or what we want a handle on, is the rotation period of the star. That's going to be the strongest, let's say, noise signal we would expect. We would expect that the strongest noise signal added from these spots rotating is the rotation period. So we can search for that in the photometry. And remember, I showed you these periodograms for anyone that's not here. These are kind of like Fourier-like analyses where we just look for the power by applying sine and cosine functions. And we can see things like this, where in this case it's a strong signal that has a false alarm probability less than 0.01%. So that's a detection of the rotation period of a star. And that's great, because if we see a Doppler signal that agrees with the 10 days, 11 days in this case, it's likely, well, I say a Doppler signal, a radial velocity signal, then now we're worried. Likely not to be Doppler in that case. But that's all good and well. We can sometimes see linear trends, linear correlations between things. What we want to do is kind of understand how to decorrelate it. How does it affect radial velocities? And this has been done. This was published by Artie Hatzies in 2002, where what he showed is, we looked at, remember I said the filling factor, the percentage of the disk that's covered by spots. And for things like the sun, we're only talking a couple of percent. It's not big. And when we get to late type, really late type stars, so say the M dwarfs and maybe at the fully convective boundary, possibly these things have higher filling factors and they're possibly more homogeneously covered. So there may be an interchange between not just the fraction of surface that's covered, but also the position of the spots. If you're homogeneously covered the disk, we don't care. You could be 50% covered by spots. If they're homogeneous and static, we don't care, because we'll get no effect on our radial velocities. It will always be static. But it's the fact that they're not. and they're down in these spot groups that's rotating that gives us a problem. So what we can do is look at the radial velocity amplitude against filling factor. And this was split into rotation velocity, so these different rotation velocities. And so one thing you can see straight away is for things that rotate slowly, the amplitude on the radial velocities is small. Hence, go after things that rotate slowly. That's one thing. And we're going to see in another slide that things that rotate slowly are just things that are old. So these stars rotate fast when they're young, and they gradually lose that. And very quickly become quite slowly rotating. However, when we move up in velocity, we start to see a much larger amplitude. Look at these numbers, and I've highlighted these numbers here. This is the functional form to fit this data. This is what we can use to estimate. But we run anywhere from 1 to 100 or hundreds of meters per second, particularly when we've got high rotation. And we'll look at this in a second. Particularly when we've got high rotation, now we're up at 400 meters per second. We're talking completely different orders of magnitude if we're looking at trying to find small planets. I mean, here I am talking about 10 centimeters per second, talking about exo-Earths, and yet I'm showing you plots where there's stars that are going to have hundreds of meters per second of radial velocity noise introduced from magnetic fields and rotation. So, again, like I say, what we can do is, there's a chromatic dependence, as I mentioned. So, we calculate this S index, this calcium H and K index, and what we can do is calculate it as a function of the basal level. The basal level being the kind of population mean or lower limit. And we can look at the excess, or the excess chromospheric activity. And we can get some lower limits then, and we call this jitter. And so this was a paper by Isaacson and Fisher a few years back where they produced some functions where we can calculate the expected jitter for stars. And this just kind of confirms what I just showed you from 2002. What we find is, because there's this kind of chromatic effect, that when we get to around the mid-K stars, so remember, we looked at the HR diagram before and we said the suns are kind of Gs, mid-Gs, now we get down to the Ks and then the Ms. And so when we get down to about the mid-Ks, we kind of almost decouple ourselves. Their effect, their radial velocity noise, is much lower than the instrumental stability that we were looking at. So actually K-dwarfs, mid-Ks, are excellent targets to go after for habitable planets. In the sense that, we'll see tomorrow, M-dwarfs come with other habitable planets around M-dwarfs, or planets in the habitable zone around M-dwarfs, may come with other problems, purely because the habitable zone is really close to the star, and the fact that they're likely to be tidally locked to the star. What kind of effects, this is for the biologists and stuff out here, what kind of effects can we expect when planets are tidally locked? What kind of thermal process are we going to see if we've just got one side that's being hammered by radiation and the other side? So we may be seeing things that are boiling on one side and frozen out on the other side, or what type of wind patterns do we have? So things like, this is something we'll talk about tomorrow. So maybe in actual fact, the kind of mid to late Ks are better targets. They're stable. Their habitable zones are a bit further away, so probably the planets, if they're in there, are not tidally locked yet. So this is just something to think about, because I keep making the case Ms are great. We're there at the moment because of the biases, they're small stars, but also we need to consider what we define as a habitable planet and what that really means under these conditions that are really different from what we've got on Earth if we're tidally locked, for instance. So what we try and do, and the reason I wanted to show this is just to show the kind of quantity we've got. I've showed calcium 2, H and K, H alpha, etc. This is one target. It was actually Proxima b. I was going to talk about it tomorrow, but I wanted to show you, Proxima Centauri, but I wanted to show you. When we were looking for the signal of Proxima b, we actually knew about it a few years ago, but when we're looking for the signal, we started to employ many different activity indicators. And we could show actually for this whole array, and what I'm showing in the x-axis here is different data sets from different instruments, UVs, and then 3 from the same instrument but different epochs, harps essentially. And we could see that actually there was no correlation. We could look for the correlation parameter between the radial velocities and all of these indicators, and we found nothing. This was one of the strong indicators that Proxima b, the small signal at a meter or so per second, was real. So I'm just trying to show you the kind of overall global set of indicators that we use, including photometry. And so I said we had a kind of handle on how to generate the magnetic field of the sun, the magnetic field of stars, where we've got this core and then we've got this radiative zone that takes up, I said, about 70% of the sun. About 70% of the sun is this radiative zone, and then the last 30% is the convective layer. And between that we have something called the tachocline, or this kind of shearing layer between the radiative zone and the convective zone. And that shearing layer is kind of what drives this big, strong kind of toroidal magnetic field that comes out and punches its way through the surface that doesn't exist, but punches its way through the photosphere and produces these spots. And so that's dependent on the rotation. It's a dynamo model. It's an interface model. It's a dynamo interface model. And so we can take the S-index, that S-index that I showed you from the calcium HKs, and we can take away the photospheric component. We can normalise it to the bolometric luminosity of the star and subtract the photospheric component so that we're just looking at the chromospheric part. And that's what the log-R HK is. The log-R HK is just the index that takes that S-index, and takes away the photosphere. And so we're only looking at the chromosphere. And when we do that, we can look as a function of time. So log age in years. And what we see is this strong correlation, as expected from our dynamo model, of this activity index, chromospheric activity index, and the age of the star. So what does that mean? Well, what it means is that if we want to look for exo-Earths, and we want to look for really small planets, we want to really look at old stars. That's what it means. It means that old stars are going to be inactive stars. And so what we really want to look at are the oldest stars on the main sequence. Now, of course, stars evolve, so they move off the main sequence, but we want to look for old stars on the main sequence. They're going to be basically the slowly rotating stars. They're going to be the most quiescent stars magnetically. And so this is another bias, remember, in our surveys, but that's okay, because this is a positive bias. This is a bias that we want to go after. We want to look for, we've been trying to look for solar systems and compare the solar system and compare the number of Earths, etc. Well, that's what we're doing. We're biasing our survey to look for sun-like stars. And the sun's about 4.5 billion years old. It's about halfway through its cycle on the main sequence. And so the sun sits somewhere about here. About a log-R HK of -5, just to give you a data point there to compare these points. And so, for instance, the survey we run, we only look at stars with a log-R HK of -4.9 and less. So this is a very common method, is to just go after, heavily biased towards the oldest stars that we can see, or the most inactive. I seem to be running quite slow here. So I just wanted to show here, and I'll give you the slides, you can go away and look at this, that we can also look at magnetic field topologies now as well for other stars. So we talked about it, we looked at the topology of the sun, but we can do that for other stars as well. And for getting all this work, I just wanted to say that inactive branch stars, these things here, the kind of stars that we're going to focus on, the inactive stuff, have shorter activity cycles. And may be linked to the fact that they're axisymmetric colloidal fields. That's their bulk field. But what to focus on is this inactive, the fact that their activity cycles are shorter. Because, of course, it really depends what type of activity cycle these stars have, what impact we're going to have on our radial velocities. If we look for something at a year, for instance, we would prefer if their activity cycles are either really short, super short, days, or they're super long, really long, 10 years, 50 years. Now, that's great, because we can deal with the impact very simply. If it's 1 year, then it's more problematic. And this is just to show that we can do this on M dwarfs as well. Now, the final thing, or say the final thing, the second last thing I wanted to show from these dynamical bodies, stars, sun-like stars, is we also have something problematic called stellar oscillations. So we're looking at that final 30%, that upper layer of the photosphere, the convective zone. And in that zone, we generate sound waves from the dynamical motions going on. There's sound waves, non-radial motion, actually. And so these things are kind of pulsating non-radially as well. And that pulsation, of course, comes along with a velocity field that needs to be taken out. And we call these P modes. The strongest ones, at least, are called P modes. There's others generated by the core, gravity modes or so. But the P modes, the sound waves, have characteristic short lifetimes. That's a good thing. So what I show here, if we look at this side, we look at the scatter in radial velocities against the type of star. So the sun's somewhere down here, minus 3.7 or so, in this log luminosity over mass space. And so what we tend to find is we see these gradients with stellar type. But we also see that signal, that RMS, that amplitude from these oscillations decreases the more we integrate. Because their power spectral density is really, it peaks at a few minutes. And so they've got lifetimes of a few minutes. So if we observe the star for 10 minutes, we can just integrate those cycles all out and really beat down that noise. So this is just to tell you that if you want to go away and observe stars, for radial velocities, for even photometry, for transits, and you want to look for the smallest signals, the small ones, then this is going to be your first problem. And so I would advise you to integrate something in the ballpark of at least 15 minutes, and you'll get rid of all the pattern, the interference from these cycles. There's also, and we've all seen, hopefully, some nice images from when, of course, we look at the sun, and we can look in the corona, and we can see things like that we call flares. We see material that's being jettisoned in various ways, and flares also must have some impact because they have light. We're collecting photons from them, and they have velocity. And so they must have an effect. They certainly have an effect on your photometry, but they must have some effect on the radial velocities. And I'm going to skip on here. This was also of Proxima Centauri. And this was a recent work by Davenport just this year. Proxima Centauri turns out to be a flare star. And a lot of M dwarfs turn out to be flare stars. They tend to jettison a lot of energy. In fact, when it flares, the XUV flux, and so it gets up to like the sun type of energies. And remember, these things are only a tenth of a solar mass. And so I just want to show you that there's a massive amount of it, or a lot amount of energy jettisoned. These things get bright at these points, really bright. And so, in this case, Proxima Centauri is thought to possibly be like constantly flaring. The flare rate is something like 6 to 8 per day that have photometric amplitudes of the transit signal expected from Proxima b. So we're trying to observe Proxima b, we're trying to search for the transit signal of the planet, and we'll look at this tomorrow. But it also flares about 70 times per day. And it's the flare timescale turns out to be something like about half an hour or so. And that means that it essentially is constantly micro-flaring. The star's constantly in a state of flare, if we call it that. And so that's going to make it bloody hard to pull out the transit signal in Proxima b that we really want. Now, what we can also do, I showed photometry, and photometry is an excellent indicator of flares, particularly. It's an excellent indicator of flares. This is data from ASH 2, so about 60 days of data or so, and this is just normalised flux in 2 bands. And we can see this characteristic pattern. 1, we can see this cyclic pattern, and 2, we can see the effects of flares, with the stars getting much brighter. And the good thing for us is that I told you about these indicators. When we look at the indicators, in particular things like the bisector, or just if we look at the width of the lines, all of those lines, if we do that, we see, 1, okay, things are impacted by flares, potentially, but the more interesting property is that we can track the same type of signal that we see in the photometry. So this is good that the indicators we're using, at least for small M dwarfs, are working. And we've proved it by looking at photometry, quasi-simultaneous photometry, and the activity indicators. And so this is good because we can probably decorrelate it. So we can probably decorrelate the effects of those spots, that magnetic activity, or that activity cycle. And that's a good thing. I just wanted to give you some numbers before I move on. I'm coming kind of to the end of this part of the class, in the sense that I've thrown a lot of stuff at you: magnetic activity, convection, rotation, and shown that all of these things are impacting our radial velocities. I showed at least the magnetic activity can be correlated by looking at the calcium HK line, or the H-alpha index, and we can look at its impact on radial velocities, the amplitude. But the other point is, I just said about 5 minutes ago that things have characteristic lifetimes. Stellar oscillations have characteristic lifetimes, but so do convective patterns. They also have characteristic lifetimes. And when I talk about convection, and we explained what convection is, when I'm talking about convection, what I'm talking about, there's 3 types, ballpark types. Granulation, mesogranulation, and supergranulation. And those are 3 different types of convection, characteristically, particularly by their amplitude, and by their size, and by their time scale. Now, granulation has time scale of minutes, mesogranulation has time scales of a few hours, and supergranulation has time scales of a couple of days, 1.5 days. Now, why is that problematic? Well, that's problematic because we can only observe the stars for a fixed limited amount of time. So it says we can integrate out P modes because their timescales are short. We can integrate out granulation because its timescale is only a few minutes as well, or on the maybe 10, 15 minutes. But these things start to become hours and days. And so we really need to understand their impact on the radial velocities if we want to really dig out the small amplitude signals. And so we can look at their power spectral densities, so frequency against essentially their strength, or spectral density. Where is all the energy emerging? And when we do that, we're doing well. We can actually model these things now pretty well, these 3 components of convection, or at least their power, their cycle. And so what the De Musk paper here would advocate, and did advocate, was that we should start to try and integrate out all 3 of these types of convection over nightly timescales. So remember, we need to win telescope time. This is a competition. And ESO, for instance, every 6 months we have to write an application, and we've got to compete with the rest of the field to win telescope time. And so time is really precious, very precious to us. Here what we're talking about is averaging things like 3 radial velocities per night in 2-hour spacings, or 2 radial velocities with 5-hour spacings. Now that's great. This is spectral type, so we're looking at binning against the radial velocity amplitude from convection, or just basically scatter of the stars for different spectral types. And what we see is that if we do that, these types of binning, that's great, we can beat down the radial velocities. But one, we don't learn anything about the star, we're just trying to integrate it out. And two, is that this is costly. It's not efficient to do this, in the sense that we're binning data, we're going back to the star again 3 times or so per night, and then binning this, so we take 3 data points with 15-20 minutes of integrations, and then bin them down to 1. So we lose a heck of a lot of information. We go from 3 velocity points down to 1. That's a hell of a lot of information we've lost there, without really gaining any knowledge about the star. So, a nice paper by Baluev in 2013 shows the power spectral density of radial velocities from HARPS and Keck. Remember, this is HARPS, the 1 meter per second instrument in Chile, and Keck, the 10 meter telescope with the iodine cell method. So this is the 2 methods, the simultaneous thorium-argon that we talked about on Monday, and the iodine cell method. And we can see that the PSDs, being different, they're different, but they're certainly not white. They're not white. I mean, we can see these things are not flat. There's peaks, there's shape. And that means that there's correlated noise in the data. Of course there's correlated noise. I just spent an hour discussing magnetic fields and rotation spots being rotating with the star. And so of course there's going to be correlated noise. And there's also instrumentation noise. How we take away the effects of the instruments. That's got a correlated parameter. Whatever level that is, we need to decorrelate it. So here we can see as a function of time and radial, let's say velocity, whatever this is, it's just noise in black and grey. That's what white noise looks like. And then you can look in, if we add some red noise, pink noise, whatever, we start to see heavy structure. That's what's shown in red. And there's nothing we can do about that unless we model it. Now, I've just showed convection, red noise is coming, and we discussed about rotation. So I just wanted to quickly show you that the rotation that we see or the rotation of the star, impacts our spectral lines. It broadens our spectral lines, and I need to go a bit faster now. In the sense that if we look at the spectral line, or a combination of the spectral line, if we deconvolve the spectrum and just have one spectral line, as velocity and deconvolve the flux, we can see that each of these 3 solid lines are that model, or that deconvolved spectrum, just being convolved with a rotational profile. Something like that. These rotational profiles, they just have like parabolic functions, they just have parabolic shapes. And so we can broaden and compare to a template, which is you see in dots, for instance, and that allows us to measure velocity, rotation velocity. But what I'm trying to get you to see, is that also rotation broadens the lines. So it doesn't only cause these spots to migrate around the star or rotate around the star, but also high rotation broadens the spectral lines. And so what is that going to do? Well, it's going to take away your precision on the centroid of the line, your radial velocity measurement, but it's also going to increase your blending factor. So your lines are going to blend more. And we don't really like blends. We want to have all these lines, individual lines, sampled, because when lines blend, we lose what's information, basically. We lose this quality factor, quality Q factor. And the quality Q factor is just defined as being something related to obviously wavelength. This is flux of photoelectrons, if you like. The rate of change of those with wavelength and some error. And this part's squared. And so what that means is if we look at rotational velocity, for instance, here against the quality factor, we can see that if we increase in rotational velocity, we decrease in quality. And I just said that quality from this weighting factor, based on a lot on this weighting factor, is the amount of information in the spectrum. So we lose a lot of information at high rotation. And I also said mid-Ks are good. They're also good for information content, for radio velocities. And if we look at wavelength as well, the same three types of stars, mid-K up to an early F, we can see that with wavelength, the quality Q factor also decreases with wavelength. And that's just because the number of lines decrease in the spectrum. And I'll not go through anymore, but just to say that it also decreases with spectral resolution. Makes sense. We're sampling the lines. The more resolution we get, the more we sample the lines, the more we can separate them from being blended, for instance. But then we can look at that against temperature, V sin I space, and we can start to build a map in temperature and rotation of how we get the best radio velocity uncertainty. This is for harps. And so potentially we can get down into this ballpark, sub 0.20 centimetres per second type of limit. Now, I think, have I got 5 minutes left or a little bit longer? Okay. I showed this yesterday, this plot, with late M stars. I said, not only are we pushing the early M stars, we're going to the late M dwarfs. And remember I said that, well, late M dwarfs are really different from what we've been looking at, because I've been discussing magnetic fields and stuff in the sense that these things are generated at the boundary between the radiative zone and the convective zone. Well, these guys that we've been looking at are fully convective. They're fully convective stars, so there's no boundary there to generate that field. So these things, we need to come up with better models for their magnetic field. But one of the interesting things is, remember I said that their RV scatter is in excess of 10 metres per second for all of them, and we discussed it yesterday and through some of the questioning. But also, if we look at the flux in the H alpha line, and one of those chromospheric lines, against its bolometric flux, or the bolometric flux of that line, we can see that with radio velocity, there's characteristic trends. So it's not only sun-like stars that show these correlations, these radio velocity correlations with chromospheric activity indicators, but also the fully convective stars show that as well. So that's a good thing. Maybe we can decorrelate those as well. And just to hammer back this point that we did say it yesterday, remember they're also rotating. So late M dwarfs should be good for playing the biases to detect really small planets because they're really small stars. But it seems the population tends to rotate. Can we deal with that? So just to finish up this part, and when I say this part, I think I'm basically going to finish here, is that I said we can integrate out a lot of these effects, particularly the convection effects, particularly the noise from the oscillations. We can integrate them out. They've got well characterised lifetimes that tend to be dependent on the type of star that it is. However, what we've been doing now is to move forward from integrating them out and try to also learn things about them. So we've been employing global models. So remember in the first class, the first talk on Monday, I said this is kind of what's been used for 20 years, or certainly 15 years. This has kind of been the model that's been used, the white noise model, where we've got some systemic offset, so we've got some radial velocity, absolute radial velocity of the star. Acceleration terms, potentially there's trends in the radial velocities from really long, distant companions or so. Our Keplerian model that we discussed and the Gaussian noise model. That's where we've kind of been over the past 15, 20 years or so. Now, so what we've been doing is to try and move forward. I showed these correlations are definitely, they're present. And we're now at the stage where they're affecting our radial velocities. We're at the sub 1 metre per second level. And I said these things are happening at the 1 or 2 metres per second level. So we've started to play around with looking at moving average models, or at least correlated noise models, to try and deal with this stuff and understand it. Where here we apply just a standard kind of moving average with like an exponential decay, so things that data that's further away is less correlated, essentially following this exponential profile. And we also put these linear correlation terms, so like the calcium HK, the H alpha index with radial velocity. We also correlate these, and that we can learn a lot from the start by doing that. But also it means that although we're increasing the dimensionality of the problem, we need to, because they're there. We need to deal with them. We're also not going to lose any information in this respect by we're going to be able to weed out small signals that are buried behind these things. I say we're going to. Hopefully we can. That's what we hope. So what does all this mean? Well, dynamical bodies like stars, I said, do not give up their secrets easily. Hence why we've got no exo-Earths at this time, but we're getting there. But we need to continue to develop these new methods. In particular, we need to start really focusing on modelling the correlated noise. That's one of the things you take away from my entire set of lectures. If you want to get into this field, I would really advise you to go along and start focusing on how we can model the correlated noise better. In fact, it may be, and a lot of people believe it is, that we're kind of getting to the point where we're reaching the stellar limit. We're reaching the noise limit of the stars themselves. That will, if we don't understand it and we don't model it, we'll never detect an exo-Earth signal in radial velocities or even transits unless we understand them. Kepler's shown that we can do it from space with transits, etc. Radial velocities, it's a bit more difficult if we can't model that correlated noise. I'm a bit more optimistic. I suppose I'm always optimistic, but I don't think we are. I think maybe it's the tail of the population, but there'll be stars that are even more stable. I think we'll get there. However, if we want to understand the population, we need to model that correlated noise. So I want to ask, can I continue, or that's been almost an hour and a half? I only have another 10 slides, but okay, let me go on. I'm sorry, I don't want to eat any people's coffee time and stuff. But okay, so this will continue tomorrow. I wanted to just look at some kind of instrumental limitations. Let me go through it quick since we're nearly at the end. And I've said a lot of this vocally anyway, I think. So one limit we're at the moment, we use thorium-argon or iodine, but in particular thorium-argon as our wavelength fiducial. That's how we set our wavelength scale or set our ruler. We need a stable ruler if we want to extract precision radial velocities. And we've been using thorium-argon lamps to do that. Remember I showed you the two fibres. HARPS is fed by two fibres, one on star and one on the thorium-argon lamp. Well, when we look at, and this is an example of a set of thorium-argon lines that we use. We have to map these lines very precisely, fit them, and we can get down to really, really precise velocity scatter. In general, over the sample, there were individual lines scatter at the level from 0 around the mean of 10, 20 or so, tens of meters per second. But when we combine all of that information, that's what allows us to get down to really high precision. But when we look at that actually, and we look at the RMS, that's what we're limited to. This is our wavelength solution. This is the fundamental limit, 20 centimeters per second. So with thorium-argon, we're not going to get by that. That's systematic noise, if you like that. We'll never get by that. So we have to move away from thorium-argon as a wavelength ruler, and we'll see tomorrow that we're doing that, and we're going to do it. Of course, we need to move it away. It's twice the amplitude of an exo-Earth. Now, the other thing is, and I mentioned on Monday, was that we need to also illuminate the spectrograph properly. So illumination variations in the spectrograph introduce velocity shifts, they introduce offsets, centroiding, etc. So the way we've been controlling the illumination pattern, well, one is of course the slit that we use. We can set the slit width to control the illumination, where, remember I said there's an atmosphere, the light's coming down and it's turbulent, it's moving. So we can set our slit width such that it matches the seeing or so. So that we're not going to get this seeing disc, this disc moving off the slit. And we can add in fibres, optical fibres. So optical fibres give you real control of how you illuminate your spectrograph and keep it really stable. But of course they have their own noise to deal with. They have modal noise. That's a function of the number of modes is a function of like the diameter, and it's got a chromatic dependence on wavelength. Keep that in mind. But one way we can get around that is to use non-circular fibres. It's got this diameter dependence, but when I say modal noise, this is what I'm talking about. So all of this kind of horrible noise pattern, these spots, we want this. We want a nice uniform illumination pattern. And so what we can do at the moment is to have like a grad student stand and kind of shake this for a long amount of time, but people's arms get sore. But we use instrumentation to agitate the fibre. And that's what we get. We end up with something that looks kind of like an illumination pattern or uniform illumination. Not quite. But we'll look at, if we move away from circular fibres, we tend to destroy a lot of that modal noise, in the sense that we get much more uniform illumination. So since I said I wanted to give some new things, well, this is a new paper that will be coming out in a few months, I would say, where a colleague of mine, Fabo Feng, he's been looking at some stars with many, many data points. And we can see these data points here. We have things from Keck, HARPS, it's mostly from HARPS, these black dots. And for this one star, there's 5 signals in this data. Now the reason I wanted to show you this is because this is where we are at the moment. Remember, the wavelength, the thorium-argon solution is 20 centimetres per second. We can't get below that. But of course we have many other problems. We've got stability of the spectrograph that I tried to show, the illumination, the centroiding and the fibre. We've got mechanical stability. However, when we look at stars that have got tons of data points, thousands in this case, we're actually able to pull out signals 30 centimetres per second. We're getting close to 20 centimetres per second. But look at where these signals are buried. Now if we have a Gaussian noise model or a Lorentz-Scargo periodogram, there's no way we can detect that. We cannot detect that. We only are able to pull that out because we can model the correlated noise in this data set using a moving average model. And in this case it's a moving average model with a couple of components, so it's got even more dimensionality. But it allows us to pull out things at about 30 centimetres per second or so. So HARPS is incredibly stable. That's one thing to take away. HARPS is incredibly stable. And that's important for tomorrow because we've already got the engineering almost. We just need the ruler. Okay, I'll finish in a couple of slides. I said flux is already a problem, and I talked on Monday that we really want to be pushing towards direct imaging. But it becomes a problem in the sense that we're looking at scales of, if we look at a firefly around a lighthouse bulb in Rio, then the kind of scales we're looking at is from Santiago, something in that ballpark. It's not an easy game to play, because I'll just quickly go through this. Something like an exo-Earth, or the Earth, is about 300 million times fainter or so than the Sun. That's not many photons to get from if we really want to detect it. But we've got, and I talked on Monday about this, we've got methods to do that. The atmosphere is a big problem. So first off, we put in extreme adaptive optics. We close that loop, we deal with this atmospheric turbulence, and most of it's low to the ground. The higher we are, the better. Most of that turbulence is in the dome, actually, a lot of it. And then we can put things like coronagraphs in place. So if you ever try to look at the moon or something standing under a street light, you put your thumb on the street light and it makes it much easier. Exactly the same technique. We stick something in there, a Leo stop or whatever, and just block out the light of the central star. And that gains us another couple of orders of magnitude in contrast. And then we can play even better games and start to say things like, okay, let's try to take advantage of the fact that the field rotates, for instance. So we can focus on an object, a star, and let the field rotate around. And things like our problems that we get from trying to remove all of these, all of this light, we call them speckles, all of these kind of dots and stuff here. They've got chromatic dependence and they don't move if the field rotates. So we can then recombine the image and we get rid of the speckles and things like planets we can pull out. That gains us another couple of orders of magnitude. And at the moment, we're something like 14 orders of magnitude. This is sphere on the VLT, so this is kind of the limit at the moment, particularly for big telescopes. We're about 14 orders of magnitude in the near infrared at about half an arc setting separation. So that's impressive, but it's not going to pick up on an exo-Earth. I just showed you that you gain 1 in 300 million in flux from an exo-Earth, so it's not quite there yet. I'm going to skip that and just leave it here with the summary. So just to say that, so we've looked at some of the problems, in particular the stars themselves. That's one of the keys. The stars themselves are not static bodies. They're big balls of gas, of plasma, and they're dynamic. They're structured. And so we're moving to understand that, the impact of that, how dynamic they are on our radial velocities on our observations. Also, like I said, I want you to really keep this in mind. Correlated noise, it needs to be considered, particularly in, well, it needs to be considered in radial velocity analysis, needs to be considered in photometric analysis. And that will be the key, one of the keys for us reaching these small 10 centimetre per second signals. So since I'm out of time, I'll leave it there and take any questions if you want, or let's go and get some coffee.